Anyone can write code that works. But what about code that's truly powerful? If you want to build something that's fast, efficient, and ready for the real world, you've got to understand a concept called time complexity. So let's dive in and break it down.
All right, let's kick things off with a super simple scenario. Picture this. You've got two programs, right? They do the exact same thing, but one of them is done in like a single second. The other one, it takes a whole 10 minutes to finish. So which one is better?
I mean, it's a no-brainer, right? We're all going to pick the 1-second program. We want our stuff to be lightning fast. But here's the thing. That simple stopwatch test doesn't actually tell us the whole story. It's a little more complicated than that.
So, how do we actually measure this stuff properly? Is pulling out your phone's stopwatch really the professional way to do it? I mean, think about it. What if that 1-second program was running on some crazy expensive supercomputer and the 10-minute one was just chugging along on a really old laptop? Yeah, all of a sudden that 1 second doesn't really mean what we thought it did, does it?
Okay, so clearly we need a better way. We need a real measure of speed that doesn't care about what computer you're using. We've got to look past the seconds on a clock and get right to the heart of the code itself.
And that's where this idea of time complexity comes in. And listen, this is super important. It is not about measuring seconds. Not at all. It's about measuring how the runtime grows. It answers one simple question. If we throw way more data at our program, how much harder does it have to work?
Seriously, just think about all the things that can mess up a simple time measurement. The same exact code will run faster or slower depending on your laptop, the programming language you chose, the compiler, even your internet speed could play a role. It's just not reliable. We need a way to measure this that ignores all that outside noise.
So, instead of seconds, we measure something else, the number of basic operations. We literally just count the steps the computer has to take. And by doing that, we get this pure, clean measurement of how efficient the code is. And it doesn't matter one bit if it's running on a supercomputer or a toaster.
Now, to have a conversation about this stuff, we need a common language. And that language is called Big O notation. You've probably heard of it. It's basically the standard way we talk about how an algorithm performs as we pile on more and more data. So let's look at a few of the big ones you'll see all the time.
All right, first up is what I like to call the holy grail of efficiency, O1, which just means constant time. Think about this. You have an array and you just want the very first element. Does it matter if that array has 10 things in it, or 1,000,000 or 1,000,000,000? Nope, it's always just one step. Go to index 0 and get the thing. That's O1.
And this is the magic of it. You can blow up the input size from 10 to 1,000,000, and the computer does exactly the same amount of work. Just one step. The workload doesn't grow at all. If you were to draw a graph of this, it'd just be a perfectly flat line. No matter how far you go to the right with more data, the line doesn't go up. No growth, no change. That's our O of 1.
Okay, moving on. The next one you'll see everywhere is ON, or linear time. This is super common. The easiest way to think about it is a single for loop that has to go through every single item in a list. The amount of work it does is tied directly to the size of that list, which we call N.
It's a really simple one-to-one deal. If you have 10 items, it takes 10 steps. 100 items, 100 steps. 1,000 items, you guessed it, 1,000 steps. The work grows in a straight, predictable line right along with the input. So the graph for this one is just a nice straight line going up at a 45-degree angle. You double the input, you double the work. It's totally predictable. And for most things, this is perfectly fine. It's manageable. And now we get to the danger zone. This is ON squared, or quadratic time. This is where programs go to die, where performance just falls off a cliff. The classic giveaway for this is a nested loop. A loop inside of another loop. Because for every single item in that first loop, you have to run through the entire second loop again. It's a lot. And the difference here is just, wow. Let's put it in perspective. For an input of, say, 1,000 items, that O of n algorithm takes 1,000 steps. Makes sense. But the O of n squared one, it takes 1,000 times 1,000 steps. That's 1,000,000 steps. The growth is absolutely explosive.
The graph here isn't a nice straight line anymore. Oh no, it's a curve that starts off slow and then just shoots up towards the sky like a rocket. This is the stuff that makes programs slow. This is what can bring a really powerful server to its knees once the data gets big enough.
So you might be thinking, okay, why does this matter so much? Why are we so obsessed with these letters and numbers? Well, it's simple. In the real world, where you have real users and just massive amounts of data, How your code scales is literally everything. Let me paint a picture for you. You've got your two solutions. With 1,000 users, your O of n solution is humming along, working perfectly. But your O of n squared solution, the one that worked just fine when you tested it with 10 items, it just breaks. You get that dreaded time limit exceeded error. It's just too slow to handle the load.
And that is why companies like Google and Amazon care about this so much. They aren't building apps for a few hundred people. They're building for billions. So when they're hiring, they don't just check if your code works. They check if your code scales.
Okay, so now that you get the why, let's talk about the how. When you're trying to figure this out for your own code, there are two golden rules that make it way, way easier.
Rule number 1, drop the constants. So if you calculate something is O of 2n, you just call it O of n. Because at the end of the day, we care about the general shape of the growth, not the exact angle of the line. And rule number 2, ignore the smaller terms. If you have something like O(n) squared plus n, that n squared part is going to get so huge so fast that the little plus n part becomes basically irrelevant. It's a rounding error. So we just chop it off and call it O(n) squared. We only care about the boss, the dominant term.
So to wrap this all up, here's the one thing I really want you to remember. Time complexity is not about how fast your code runs on your laptop today with a tiny bit of data. It's about being able to predict the future. It's about asking yourself, what happens when this thing gets massive? And being able to answer that question, well, that's what makes a great programmer.